Scientists agree the major driver behind the rise in global greenhouse gas emissions is human activity. How does farming fit in? What is the contribution of animal agriculture, and how are these values calculated?
The consuming public is more and more interested in where their food comes from, what's the carbon footprint.
What's the carbon footprint? Or what's the environmental footprint of a gallon of milk or a pound of beef or a pound of chicken meat?
My name is David Schmidt, and I'm an agricultural engineer at the University of Minnesota and regional coordinator for the national project Animal Agriculture in a Changing Climate. There's a significant amount of miscommunication about the role of agriculture in climate change. Some say that animal agriculture is the largest contributor to greenhouse gas emissions, while others deny any contribution from animals. The answer lies somewhere in between. The objective of this video is to provide you with a solid foundation of how emission estimates are calculated and the real contributions of animal agriculture to U.S. and global greenhouse gas emissions.
Carbon is all around us. It is the fourth most abundant chemical element in the universe, behind hydrogen, helium, and oxygen. The biggest reservoir of carbon is stored in rocks, approximately 66,000 gigatons, with 1 gigaton equal to 1 trillion kilograms. The second biggest reservoir is the deep ocean, and the third largest reservoir is in fossil fuels. The atmosphere and the surface ocean are the smallest carbon reservoirs, but possibly the most important. Carbon is moving between these reservoirs constantly because of a variety of chemical and biological processes. This is known as the carbon cycle. The total amount of carbon that cycles in and out of the atmosphere naturally each year is about 210 gigatons. The arrows and yellow numbers indicate this movement or cycling of carbon. Plants and oceans are referred to as net carbon sinks because they absorb more carbon from the atmosphere than they emit. These carbon emissions occur in the form of plant respiration and chemical exchanges with the ocean. The red numbers indicate the human influence in the cycle, also known as anthropogenic emissions. They can mostly be attributed to the burning of fossil fuels and changes in land use. Human activities contribute 9 gigatons of carbon emissions annually. About 2 gigatons of that carbon gets taken up or absorbed by the ocean. 3 gigatons of that carbon gets absorbed by plants through photosynthesis and taken up in the plant soil system. All this movement results in an annual net increase of about 4 gigatons of carbon going into the atmosphere each year. As you can see in this diagram, the amount of carbon dioxide in the atmosphere was relatively stable for hundreds of thousands of years, at an average of around 230 parts per million. Then, about 100 years ago, the CO2 concentration in the atmosphere began climbing to where it is now, about 400 parts per million. This animated diagram more dramatically illustrates the rise in carbon dioxide levels in the Earth's atmosphere in more recent years, since 1979. The numbers on the left and right indicate the CO2 concentration in parts per million. Again, this indicates the current CO2 level reaching up to and even beyond 400 parts per million. While we do not intend to focus on all of the greenhouse gases in this lesson, it is important to note that carbon dioxide is not the only greenhouse gas. The most common greenhouse gas is water vapor, followed by carbon dioxide, methane, nitrous oxide, and fluorinated gases. Excluding water vapor, the combined sources of carbon dioxide, primarily from fossil fuel use and land use change, make up about 77% of the global greenhouse gases. Because these other gases trap different amounts of energy per molecule of gas, scientists have normalized the data into something called carbon dioxide equivalents, or CO2 equivalents. This equivalent refers to the equivalent heating potential of the gas. This is also known as radiative forcing or global warming potential. For instance, a single molecule of methane will trap approximately 25 times the amount of energy as will a single molecule of carbon dioxide. So methane has a CO2 equivalent of 25. Nitrous oxide has a CO2 equivalent of 298. This use of CO2 equivalents allows us to evaluate the impact of the gases on the environment, not just the amount of these gases in the atmosphere. Anthropogenic greenhouse gases are emitted by many sources and from every country. Together, these nations contribute a world total of 45,000 million metric tons of CO2 equivalents. This graph shows percentages of greenhouse gas emissions by country in 2012. The United States is currently the second highest emitter of these gases, contributing about 15% of the world total. The highest emitting country is China. However, this same information can be evaluated based on emissions per capita. This breakdown shows the U.S. at about 19 tons of CO2 equivalents per year per person versus China at 7.5 tons of CO2 equivalents per year per person. Taking a closer look at the sources of greenhouse gas emissions in the United States alone by economic sector, we see that agriculture contributes 9% of total emissions in the U.S. Total emissions in the U.S. add up to approximately 6,673 million metric tons of CO2 equivalents. Agriculture's 9% represents about 515 million metric tons of that amount. Looking at the agricultural sector itself, we can see that agricultural soil management is the biggest source. It accounts for about 50% of total agricultural emissions. This is followed by enteric fermentation at about 32% and manure management at 15%. Now looking at the type of gases emitted, about 55% of the agricultural emissions are from nitrous oxide, which is produced naturally through the microbial process of nitrification and denitrification of mineral nitrogen in the soil. The remaining 45% is from enteric methane or from methane formed during the microbial breakdown of manure. Note that these emissions are only the direct emissions of greenhouse gases occurring on the farm. Other emissions that would occur off-farm, like emissions from fertilizer production or electricity used on the farm, are not included in these numbers. We can also look more closely at emissions by animal species. In this chart, you can see the comparisons between beef cattle, dairy cattle, swine, poultry, and all other livestock. These differences are primarily a function of total animal numbers and the contribution of enteric fermentation. Again, these are direct emissions for animal production and do not include emissions from the production of things like animal feed.
Overall, if you look at all animals in the United States, for example, the beef sector would have the greatest impact on carbon footprint of this nation, but that's only because there are so much more beef animals than dairy animals. We have 90 million beef animals and 9 million dairy cows, so 10 times more beef animals.
However, a better way to think about greenhouse gas emissions is in terms of emissions per unit of production. We can look at kilograms of CO2 equivalents per kilogram of product produced or product consumed. This evaluation includes not only direct emissions from the farm, but also the emissions that occur after the products leave the farm. We will discuss this further a little later in the video. This graph compares the greenhouse gas emissions of several products on a per kilogram basis. Of all the products, lamb is the highest emitter per kilogram of product consumed, and beef is the second highest emitter at 27 kilograms of CO2 equivalents per kilogram of beef consumed. Dairy is much lower in emissions, with 1.9 kilograms of CO2 equivalents per kilogram of milk consumed. Before getting further into attributing emissions to different sectors of animal agriculture or to different sources on the farm, we'll look at the system used to measure and calculate these emissions.
There is a way to quantify, let's say, greenhouse gases. This quantification method is called an LCA, life cycle assessment. It has been done for many years, and it has been done by many different groups using different methodologies.
The life cycle assessment, or LCA, is an accounting method that tracks all of the greenhouse gas emissions produced by a given process, product, or system. Often this is called a cradle-to-grave analysis because it encompasses all of the emissions in the life cycle of the process, product, or system being analyzed. This includes anything from the extraction of raw materials to the final disposal of the end product. Animal scientists, engineers, and others can further describe the scope and mission of the LCA as it relates to animal agriculture.
Basically, the life cycle assessment looks at the entire life cycle associated with a product. Let's say if McDonald's or Walmart or some other chain were to ask me what's the carbon footprint or what's the environmental footprint of a gallon of milk or a pound of beef or pound of chicken meat produced by your company, then most producers would say, I have no idea. But a life cycle assessment allows you to do just that. It allows you to look at the entire life cycle impact of that product. For example, the carbon footprint of a gallon of milk includes not just enteric gases that come out the front end of the cow, or methane or other gases that come off the manure. It includes everything. Herbicides and other chemicals applied to crops, the crops themselves, the soils where the crops are grown, the animals, whether it's enteric gases or manure gases. It includes the cooling of product, the transport of product, and so on. Everything from cradle to grave of this product, the true life cycle of this product.
Life cycle assessment is a systematic approach for primarily accounting for environmental impacts. It is a systems scale analysis of any product or service, really. In the dairy industry, what it means is to divide the system into supply chain stages, typically. In each of those stages, we would have what we call unit processes that have material and energy flows, inputs and outputs from other unit processes, as well as inputs or outputs from nature, so emissions to the soil, water, or air. And the process of LCA looks from cradle to grave.
Dr. Thoma's analysis in 2013 of greenhouse gas emissions from the production of milk in the United States looked at the entire life cycle of the milk supply chain, starting with the production of fertilizer to grow feed for cows through the consumption of milk and disposal of milk packaging.
So if we're talking about just the dairy farm, so that would be what we might consider a gate-to-gate analysis, then we would be interested in what happens just on the farm. That would not be considered a full life cycle assessment. So when we did the carbon footprint for milk, we literally had to account for the coal, the transportation of the coal, the construction of the power plant, the losses in the transmission lines to run the refrigeration units at retail. So all of that is accounted for.
This table from Thoma's LCA shows the breakdown of greenhouse gas emissions across the milk production supply chain. The colors represent the 4 different types of gas emitted by each stage in the cycle, from feeding the cows, enteric fermentation, manure management, all the way through to the consumption of milk and disposal of packaging. The pie chart further illustrates the percentage of each activity's contribution to milk's carbon footprint. Thoma's analysis found that the CO2 equivalents produced by each kilogram of milk consumed ranged from 1.77 to 2.4. This is about 17.6 pounds of CO2 equivalents per gallon of milk consumed. 72% of those emissions occurred before the milk left the farm gate.
So from the extraction of coal, say, for the electricity that may be used anywhere in the supply chain, all the way to the emissions associated with wastewater treatment for wasted milk that goes down the drain, or the plastic container that ends up in a landfill and may generate methane. So all of those emissions across the entire supply chain we attempt to account for, tally them up and say then this is the impact.
Thoma applied the same system to an analysis of greenhouse gas emissions from pork production. This study took into account all of the activities in the pork supply chain that contribute to emissions, from electricity and fuel to manure and waste, across all stages of production, from the sow barn to the consumption of the pork products produced. The LCA showed CO2 equivalents at an average of 8.8 to 11.6 kilograms of CO2 equivalents per kilogram of pork, from production to consumption. This can also be calculated as 2.2 to 2.9 pounds of CO2 equivalents per 4-ounce serving of pork. Approximately 60% of the emissions occurred before the product left the farm gate. While the LCA is widely accepted as the most useful and accurate tool for estimating a farm operation's environmental impact, there is some interest in learning about farm-specific variables that might affect the results. Do differences in farm size, manure handling, farm practices and technologies, soil conditions, regional climate systems, and other farm factors impact the emissions?
When we looked at this in various ways, what wasn't clear was, small farms are not as good as big farms. We saw small farms that were down in the 0.8, 0.9. We saw large farms that were in the 1.7, 1.8. So our conclusion from that was that it's not what you're managing, but how you're managing it. And so the implementation of best or beneficial management practices and care of the animals, care in the ration formulation, all of these things contribute to the better performing farms.
Dr. Thoma's LCA for pork production found some effect from manure management. Farms using anaerobic lagoons had slightly higher emissions than those using deep pit systems. As noted in the Thoma report, a full LCA encompasses many variables, and with each variable there are some assumptions to be made. How was the electricity used on the farm produced? Was it coal-based or nuclear? Was the corn grown for feed irrigated? If so, what energy source powered the pumps? What was the animal diet? How many piglets per sow? How far away is the slaughter plant or the consumer market? Was the meat cooked on a gas stove or electric stove? How much of the final product was wasted, either in cooking or off the plate? All of these variables must be assessed and generalized for this kind of study. Scan-level LCAs are used to help pinpoint the main emission areas of a product or process. For swine production, about 23% of the emissions are at the consumer level and 62% on the farm level. These farm-level emissions are split primarily between manure management and feed production. This information helps the industry and individual producers target any emission reduction strategies. Helping farms perform better is the ultimate goal of the LCA. International standards have been developed for conducting an LCA, which is important so that farmers, regulators, and others can get a clear picture of farm product emissions and identify what could be done to reduce these emissions.
Once you know what the LCA impact is of your product, then you really know where you are, and if you feel you're too high, then you can compare to what it would be if you were to make changes so that you can reduce. But if you don't know where you are, you have no idea where the changes will work. So this is why it's so critical to have good assessment methods, because they help you to know where you are. The analogy is you driving on the interstate with a car that doesn't have an odometer. You have no clue how fast you're going, but you see speed limits everywhere. So you have no clue, am I going too fast? What am I doing here? That's where the industry is right now. There are regulations, some of them very strict, for example in California, yet the producers don't know, am I complying, am I not complying? Where shall I go? Where's the goal pole? They don't know. That's a situation that is untenable. And the public is exerting extensive pressure. The legislature is, regulatory agencies are.
There's nothing simple or straightforward about tracking greenhouse gas emissions and global carbon cycling. It is also clear that no process or product is entirely responsible for these emissions. It is a combination of both natural and human activity that can be evaluated on a global scale or on an individual product scale. We are all aware of the value of agriculture as we look forward to the challenges of feeding an ever-growing human population. However, we must also understand our role in the production of greenhouse gas emissions. Thanks for learning about this important topic.